Okay, now let's move on to talk about logarithmic equations. Okay, now oh, just by the way, then on Monday, when we talk on the transformation, we are completely done. And until February 11th, there is a time that every session we practice solve problems in order to make sure that by February 11th, you have seen all sorts of problems in the logarithms and exponential functions and equations. Now, okay, let's start to solve the logarithmic equations. Now, we did, I should say, a very simple one, the last session that we meet. Now, we are just going to focus on some approaches how to solve a logarithmic equations. If you remember, from level 3, you had a concept of, for example, you had a concept of exponential equations. You had, for example, I'm just going to start it by, for example, by some geometric shapes. For example, you have squared raised to a power g of x. It was equal to, for example, a triangle. By these geometric shapes, I mean a different base. Raised to, for example, the exponent of h of x. And all the things that you saw in level 3 was focused around the fact that you play smart, make some tricks in order to transform this kind of, I should say, equation into a form that each base looks exactly the other one. Then from both sides of the equality, instead of having two different bases, then you convert everything into simple base. And for example, imagine that still they have g of x and h of x. And from that thing which we did on level 3 was that we confirm that as long as the bases are the same, now we can say that the exponents also can be the same. Then as a result, an exponential functions very simply turned into a linear equation. That was the thing that it was our focus when we did math in level 3. However, there was a problem in some instances. For example, as an example, remember, for example, you had this one. You had, for example, 2 to the power x plus 1 equals to 1 over 8 to the power, for example, x plus 3. This kind of example was the one which we saw in level 3. It was so easy because you saw that we could transform this one as to 2x plus 1 equals to 2 to the power minus x, sorry, let me erase this. 2 to the power minus 3 times x plus 3. And you saw that. This is from level 3. You saw that now as long as the bases are the same, we can convert that these two exponents, they can be equal. That was the thing that we did level 3. The base is the same. Now, in level 4, you are going to deal with the type of the exponential functions and logarithmic functions that we do not see it possible to conform the bases to look like exactly to each other. For example, we did one, I should say, on the previous session. Look at these exponential equations. We have 3, which is raised to the power 2x minus 1, equals to 4, which is raised to the power x plus 2. Look at this exponential equation. First of all, when you look at this, you see that this is an exponential equation. First of all, because we have to identify what kind of an animal we are dealing with. This is exponential, this is quadratic, this is a square root, or what it is. Because you see that the x's, they are showing up as an exponent, then we see that that's an exponential function. Okay, now we are dealing with an exponential function. What is next? What kind of a strategy we have to solve it? We have two strategies. If you remember from also level 3. Strategy A. strategy A was to make bases look the same, bases similar, like the one which we talked and solved on the previous slide. Strategy A, that's the old one from level 3. But is it going to be relevant here? Because I'm lazy myself. When I deal with the equations, I always look first to see that if the bases can be the same. If that's the case, then it's easy. Now, I'm going to ask myself, is it possible in this expression, I make the bases looks like each other? I have one base 3, I have one base, this is 4. Is it possible to do so? Impossible. How can I make sure that 3 becomes somehow looks like 4? It's impossible. Then as a result, I have to just go to choose strategy B. Then whenever we see that the bases cannot be conformed to look like each other, we just go to strategy B. In strategy B, we are going to learn it today. We say that if the bases are not similar, I'm going to use the logarithmic operators. What does it mean? I say that I look at the equation which I have. I'm going to take, for example, you remember in the algebra, as a side note, let me make it here. You remember that, for example, if f of x equals to g of x, it can always, without any exception, go to find a real number if it's not being equal to 0, like alpha, multiply both sides of the equation by that number, and still we get the same equation. The equality is going to remain valid. Now, we are going to go back to the equation, and we say that the concepts of the logarithm at an arbitrary base. Look at that, the base of the logarithm, I just put some line there. It means that the base is arbitrary. You can pick up any base. You can pick up the base 10,000, the base, guys, please mute yourself if you're on the. Okay. Now, we said that now instead of using the alpha as a real number, which comes to be multiplied on both sides of the equation, and still make the equation valid, I'm just going to use instead of alpha a logarithm with any arbitrary base. This one means that the base is arbitrary. Arbitrary. Imagine that's the right spelling. Arbitrary. It means that you can choose any base. But we normally prefer the base to be 10. Prefer 10 or E. As we saw yesterday, what was E? If that's the case, instead of multiplying alpha to the equations that we have here, imagine I'm going to multiply logarithm with the base, which I'm just going to choose it myself. What is that going to happen? I'm just going to rewrite it here. I had 3 raised to the power 2x minus 1 equals to 4 to the power x plus 2. It's not a very right way to show that, but in order to make it tangible, I'm going to show that in that way. Plus 2. Now, I'm just going to act the logarithm at the base 10 as the alpha, which I used to multiply that, Caitlin, to alpha, to f and g. Now, if I do that, I'm just going to act logarithm as an operator to both sides. What's going to happen? The first thing is that I'm just going to have the log at the base 10 with the expression which is 3 raised to the power 2x minus 1. The same thing, like alpha, log is going to act also on the right side. Log of 4 to the power x plus 2. That's going to be strategy B. Acting logarithm at an arbitrary base to both sides of the equation. Now, look at this one. Now, when you are there, 70% of the problem is solved when you take the logarithms from both sides. The remaining 30%, Jaya? Yes.
Do you need to write the 10 there, or is that necessary?
If I do not write it, it means that this is 10. Because if you remember, we said that we can either write it or skip 10. So just for 10.
I can just not write it.
That's right. If you just write only the log, it means that this is 10. Good question. Now, the rest of 30% that is left is that now that we have the logarithm, we use the laws of the logarithm. What were the laws applicable here? Look at this. I'm just going to remind you of the law that it's going to be relevant here. We had 4 laws, which was very important. The 4th one was this: the law of a function f of x, which is raised itself to an exponent n at a base a. Base can be anything. We learned that we can just take n from here and bring it back all the way as an exponent. Then becomes n log of f of x with base a. That was the thing that we discussed. If I come back to this slide, I see that I have something relevant. Look at these 2 things. These are the exponents. It means that I can use that identity and remove them all to show up as a coefficient. It means that then as a result, I can write 2x minus 1 times log 3 base 10 should equal to x plus 2 times log 4 with the base 10. That's it. Now, you see that. Now, before we continue, let's analyze the items that we have there. We have 2 items here. Let's pick up this one. Log of 3 with the base 10. It seems that it's just a number based on the things that we learned. We can put it on the calculator, log 3, and it gives you a number. It means that these things are known for us. The only thing which is a problem for us is the x, which needs to be solved. How to do that? We go back to the basic algebra. We have to isolate x on one side of the equation. In order to do that, then it's easy. The first thing we can do is that we expand these logs into each term. Then we isolate x. Guys, I'm just going to erase this part on the top because I don't want to go to the next page. I'm going to do it here with a different color. Let me choose a color distinct from it. Let me use this. Then I'm just going to go all the way up there to solve it. Now, I distribute log 3 base 10. It becomes 2 log 3 base 10 multiplied into x minus log 3 base 10 equals to, I'm going to expand log 4 base 10 into that term. Then becomes log 4 base 10 exponent, not exponent, so what I'm talking about, the x plus 2 times, because I multiply 2 to log 410. Now, guys, look at this. Look at these 2 terms that we have x's. One term is this, one term is this. And look at that, 2 times log 3 over 10. This is like a coefficient itself. Log 4 base 10, that's a coefficient itself, like 3 times x, 7 times x. Now, What needs to be done right now is that to isolate x, it's a basic algebra. I decide, because that's what I have been doing for over 40 years. I prefer to keep x on the left and the numericals value on the right. Then I'm gonna take 2 times log 3 base 10 on the left side, bring log 410 to the right side. What does it mean? It becomes then 2 log 3 base 10 x minus log 410 x equals to what? I take log 3 base 10 to the other side. Becomes positive log 3 base 10 plus 2 times log 4 base 10. Now, what I'm going to do is now, because the original plan was to isolate x on one side, I'm gonna factor it and just keep it isolated. How to do that? I'm just going to rewrite it like that. I factor x, then I have 2 log 3 base 10 minus log 4 base 10 multiplies to x should equal to log 3 base 10 plus 2 log 4 base 10. Let me erase a little bit. Now, we are done. Why? Because you see that. Now, we have been successfully isolated x in one side of the equation. What's going to be next is that I'm just going to divide both sides by the coefficients of the x, which is going to be log 3 base 10 plus 2 log 4 to the base 10 divided by the coefficients of the x, which is 2 log 310 minus log 410. And that's it. That's the x that we have been trying to solve it. You see? Then the key thing here is that I give you a couple of minutes to write, then I explain further. What time the quiz ends today, guys? 11. Oh, time flies too fast. Because today's Friday. Friday is the best day. That's why the time flies so fast. Any questions? No? But guys, you see that the most important thing is that to identify, you cannot change the bases to make them look like each other. Then use the logarithm as an operator acting on both sides. And the rest is the laws of the logarithm that we have worked on it before. Yes, Caitlin? Awesome. Now, any questions, guys? No? Let's go to the next example. Okay, let's solve this. E is raised to the power x squared equals to 200. This is a very easy one. So I'm just gonna go a little bit faster on this example and the next, because make sure that we have covered enough examples. Then while you are gonna do your homework, during the weekend you have enough, you have solved enough examples. Now, look at this one. The same problem. We have the basis, and you may ask yourself, it is impossible to make e a number to become 200, or 200 becomes a factor of e. It's impossible. Then we take the logarithm with an arbitrary base. Now, I'm going to say take the logarithm from both sides. However, here there is a trick. We say that the logarithm with arbitrary base, we can take the base as 10, as we did before. But look at the one which we have here, e. And that's why I'm just going to go on to take the logarithm from both sides. I'm going to tell you the trick when I solve it. I say the left, I have log of e raised to the power x squared equals to log of 200. Now, the question for us is this. What is the choice for the base? What do I do? Should I choose 10? Should I choose 2? Or anything? I say, look at this. This is the only case that we are very peculiar about this. We say that look at the e. Yeah, if I choose base as e here, then it reminds me. That's right. Then it reminds me, as Ash said, it reminds me of this identity, that the log of a, if the base is also a, it is always equals to 1. Then you see that you have a logarithmic expression. It can vanish into 1. Then that's what I did. I choose logarithm with the base. Some of you who are artistic and you like more art, you see that, oh, wait a minute, I can replace log with the base e into ln. It may look much better. That's what I'm going to do. Then as a result, I'm just going to write ln of e to the power x squared equals ln of 200. The log e is replaced just to the ln. And now, what I'm going to do, look at this. That's the exponent. And the identity, we know what is that. It's as a hat, it falls behind the logarithmic function. It means that then, as a result, it changes to the x squared ln e equals to ln 200. And the question which I have for you all is that, what is the ln e? 1, that's right, because ln e, it is like logarithm of e with the base e, which is 1. Interesting, huh? Then you see that if that's going to be the case, the ln e, it becomes 1. Then as a result, it simplifies further into x squared equals to ln 200. What you need to solve is for the x. How much is the x? Plus or minus square root of ln 200. Then you use your calculator, you pick up your calculator from your pocket, and you say, okay, let me just put square root of ln 200. Plus or minus, voila, the answer is there. Yes. You got the same thing. Yeah. Focus in my heart. Yeah. That's what I love. That's also good. I love it. Right hand is also. Great job. Great job. Now, any questions, guys, on this? No? Take 30 seconds only break. Just do some stretching. We continue. Just 30 seconds. Yes.
Why on ingredients? I don't remember anything. That's so long.
Fantastic.
I think we did that.
Yeah. What's the definition of average bond enthalpy?
The average energy, required to break one mole of bond in gasoline.
Yeah.
Yeah, was that right? Oh my God.
I think it's three bonds in one mole of
Oh, molecule.
Yeah. Do you know that? You do? Oh.
We don't?
Why are you guys stressing too much about this with
Yesterday, I was like accidentally on like.
Right, let's go back to the
because, like, I
equation.
bar, and then he started getting
Okay,
so mad
now.
at me. He was like, "You're not supposed to be there." And I'm like, "I don't even know what this is." Like, I like. What?
Okay,
Yeah, and then he literally gets the time, so he started like reading the definition for me. He's like, "Don't do that on your own time." Sorry.
Yeah.
this is another definition.
Yeah. Also, like, it was.
Okay, guys,
Literally every time I say.
let's solve this one.
Yeah. It's weird. Even fast. No, I don't think this is.
Okay, let's solve this one. This one we can approach there from two different approaches. We can solve it from two different approaches. We're gonna do both. You see both of them from both sides. We have the same base. The base in everything is different number, E, and E.
Is that a multiplication between the two E's on that one side?
That's right, they are multiplied. Okay, let's solve this. Some of you think, okay, hold on a second. I can see something very familiar from last year, and that was this identity, that we have base the same, but the exponents are different. Then what we learned was that we just add the exponents. And you see here on the left side, I have the same phenomena. I have the bases that they are multiplied. Then I can replace it only with one base and add the exponents together. But I'm not going to do this now because I'm just going to show the laws of the logarithm as a practice, that I'm not going to add these exponents together. I'm going to take the ln from both sides. Now, what I'm going to do is this. I'm going to just use the operator logarithm to act it from on both sides. I say the log of e to the power 2x plus 1 times e to the power minus 4x equals to log of 3e. You remember we said that the base is always arbitrary. But what do you recommend me to choose as a base here? E, that's right. Because along the way, we expect to end up to see this identity, the log of e with base e, which is L and E should be equal to 1. We are hopeful to see this somewhere. That's why we choose the base as E. Now, when we are there, and I hope that you do the same thing when you do your homework, to record yourself, to explain it like that, we see that the left side, it reminds us of this identity, that the log of a product, for example, the log of A times B with the space A equals, you decompose that into log of sums. the log of A base A plus log of B base A. That was one of the first identities in the laws of the logarithm that we learned. Very important one. Then I can detect something like that happens on the left side of the equation. I'm going to use it to decompose them. And instead of log E, I'm just going to write ln. It means that from here, I'm just going to reach to this line. Then the ln of e to the power 2x plus 1 plus, look at this. I decompose it into the sum of the logs. The ln e to the power of minus 4x equals to ln of 3e. Oh, hold on a second. We have the same thing. For 3e, this is 3 times e. Look at this one, the 3. The log with the base e of 3 times e, it's essential log 3 times e. The same identity is valid. Then I can decompose this to ln e plus ln 3. So far, so good, everyone? Everyone is happy? Now. Oh, now here. Yes.
Why do you have to convert ln if you can just automatically decompose it from log e to 1?
You mean this one?
Yeah, like I don't understand why you have to go through like ln. Like, what's the point of changing it that way?
Oh, from log e to ln?
Yeah.
Because they are the same. Log e. No, just coming back. Look at that. If I have log of a with the base e, it's as if you are artistic, you change it to ln. It's nothing, no difference.
I don't know why do we do that.
It could because it is more scientific. In any books or any papers, nobody writes log e. Everyone writes ln.
Oh,
That's the thing, because never you see in any textbooks, somebody has the log with the base e. They change it to ln.
okay.
And that's a kind of a preference to write it, but the concept and the math as is the same. Good question. Now, on the left side, I see something very familiar, which we have seen before. The log a raised to a power n at the base a, it's equals to n log of a with the base a. And I hope that while you do your homework in that recording, you follow the same thing which I do. You explicitly talk about the identities that you see. Then as a result, look at this. These exponents, they can all fall off as a coefficients behind them. Then as a result, we have 2x plus 1 times ln e plus minus 4x times ln e equals to ln 3 plus how much? That's right. ln e is this one. It always 1. That's what I told you. We expected to see something like that along the way. ln e is always 1. Wait a minute. Something weird is happening here. Look at this. I have ln e here, ln e there. It's supposed to be 1. Then it means that the next line, I can write 2x plus 1 minus 4x should equal to ln 3 plus 1. And this one is the most easiest equation that we can solve because ln 3 is like a number. For example, 3.2. Then we keep it there like that. We do not change it. Then if you wanted to know what is the x, 2x minus 4x becomes how much? 2x. You have 1 from here, 1 from there is gone. Then you get only equals to ln 3. Then x equals to minus ln3 divided by 2, and that's, we are done. Make sense to everyone? Any questions? Easy peasy? Okay. We have 2 more to go. Hopefully we can finish it today before we leave. You know that the lectures is being recorded. The slides is also saved. I'm going to put that on the Google Classroom in case if you want to go back to watch that anytime before the test. No problem. Now, we go to the next exercise, which is a comparatively simple one. We have the log of x plus 6 minus log of x plus 2 equals to x. Sorry, the log of x. This one is a different type of the logarithmic equations because you see that the logarithm is just already there. You do not need to use the logarithm as an operator acting that on both sides of that equation. The log is already there. When it is that, step number 1, which we had to just impact the log on both sides, is already done. Then now we have to just use the log of the logarithm. Those 4 important ones that we talked to just simplify them. When you look at this one carefully, you see that on the left side, there are 2 log expressions that they are subtracted. Then you see, wait a minute. It looks so familiar because I remember I have done this identity number 2 almost since 2 weeks ago, that the log of A over B at an arbitrary base A, it can be decomposed to log of difference. Then it means that if I see 2 logs that they are subtracted, it means that I can just do what? I can write them as one single logarithm like that. Then it becomes the log of the first expression that we have, x plus 6, divided to the second expression, which is x plus 2. The base of the log remains the same as it is 10, equals to log of x. Now, interesting. What to do now? We have, look at this one, guys. We have the log of 2 expressions. This is very important, that these 2 sides, you see log on the left, log on the right, and you have to also take care that the bases of each is the same. Both of them are 10. Then it means that if both sides, they have the logarithm, the basis is the same, it means that the function itself, they're going to be the same. Then as a result, we say that, I'm just going to put that as a theorem also. Then it means that, say what? That's right. We do not use the term cancel. We just infer that the functions is going to be the same. It means that not you remove, or as I said, you cancel the log, or you remove the logs. It becomes x plus 6 over x plus 2 should equals to x. And now you see this function is so easy to solve it. You have to solve this equation. Multiply x to the denominator equal x plus 6. I'm not going to do that because it's going to be very simple. You can solve it from here. Anybody who has a problem to solve this? You multiply x to this and x plus 6. Everyone is fine? Yes? then we just deduce this identity. That if log of f of x at the base a equals the log of g of x at the same base, we can conclude, the conclusion is from both sides, that f of x equals g of x. And guys, look at this. That's very easy to remember it all the time. Look at this. This expression, this theorem that we have done it so far like this. Previously, we had f of x equals to g of x. We said that, okay, if that's the case, I'm gonna take the log from both sides. Then the log of f of x equals the log of g of x. It's also true vice versa. We said that if log of x equals to log of g of x, it means that f of x should equal to g of x. That was a very simple thing that we used it for this exercise.
Oh, then can you actually solve that one?
Yep, the one there, yeah. Look at this. In order to solve it, you see that it comes with the base as 1. Then what do? Is this. We say that x times x plus 2 equals x plus 6. I use the cross. I multiplied x to the denominator, x plus 6 to the other denominator. Then what do we have? You multiply x, you expand x to all these terms. Yes, Ash, so far so good?
Yeah.
Then what do we get? We get x squared plus 2x equals x plus 6. Now, it seems somehow similar to the quadratic equations. I'm going to take x to the other side. Then I write x squared plus 2x minus x becomes how much? Plus x. And I take 6 to the other side, becomes minus 6 equals to 0. Right? You can rewrite it like that. Either you use the quadratic methods or write it as x plus 3 times x minus 2 equals to 0. Right, Ash?
Yeah.
That makes sense to everyone? Then x is either minus 3 or x is equal to plus 2. Make sense?
Yeah.
Awesome. Good question. Now, we go to solve the last equation, then we are done. Yes.
Can you go back to the last part?
Sure. No problem. We have reasonably, we have solved enough logarithmic equations today. But from Monday until the step 11, we have time to practice, solve as many problems as we can. And when you just go for the summative test, you see, oh my God, that's nothing. I have done everything, even beyond and more. Jay, is it good? I go, yeah, just like. Thank you. Let's solve this one. This one is very interesting. The log of 3x plus 2 plus log of x minus 1 equals to 1. Guys, give it yourself 2 minutes. In the 2 minutes, start slowly to think of it. It's good because at the same time, you can have some rest and solve this one. Then I solve it before the leave. Yes.
I was like, it's not related to that question, but it's related to another question.
Yes, thank you. Right, I'm gonna solve this. And let's see, I'm gonna two approaches for this. First of all, you see that on the left side, there is a familiar identity, and that's this identity that we work. We notice that the log A plus log B should be log of the product. Then as a result, you see that on the left side, you have the same thing. You have two logs, share the same base, then you say, let's make them what? Make the product of it, which means that you log, right, as log of 3x plus 2 times x minus 1. Oh. Now, this case, you see that. Now, you can write it as equals to 1. From here, we may have two groups of students. Now they say that, okay, from here, because I know if the base is not written, it means that the base is going to be 10. We have now two dividing students. One class of students, they say that, okay, I'm going to solve it based on the fact that I know that if I have the log of A with the base A equals to B, it is the definition of the logarithm. You change the image from the logarithm to an exponential function. You say that the A to the power B gives me the A. Remember, I should say the counterclockwise move. A is raised to the power B, then it gives you the answer this way. Then those students, they say that, okay, our approach is gonna be this. I say method 1. We say that 10 is raised to power 1. It gives me 3x plus 2 times x minus 1. This is the class 1 students. They say, okay, we prefer to solve it by knowing this identity, which was a conversion from the logarithm to exponentials. The second class of students, they say that, okay, now we feel more comfortable if we still stay with the logarithmic representation. But how is that possible? Because the right side, look at this. This is a number. This is not a logarithm. Everyone, please listen very carefully. This is the important 30 seconds of the class. We see that we have 1. We just want to stay still inside the logarithmic representation. But how can possibly 1 represent the log? We say that, remember this identity, that we said that the log of A at the same base is 1. Then I can rewrite this expression that I have, which was log of 3x plus 2 times x minus 1. Instead of 1, I write log of 10. You see? Because instead of 1, I wrote log 1 becomes log of 10 over 10. Then as a result, we got back to the same idea, which we had before. Log of f of x equals log of g of x means f of x equal to g of x. Then it means that as long as the bases are the same, I can conclude that 3x plus 2 times x minus 1 should equal to 10. That's exactly the same thing. Compare here, 1 with 2. You see that both of them are the same. There were two different approaches then to solve this. And the beauty of that was that sometimes you can change the numbers to a log by doing that a log of A with the base A is 1. And by doing that, it seems that we're done for today. Very fast-paced class. We have 2 minutes. If you have any questions, Daniel, you have a question. I'll come to you then. Please ask your questions. Otherwise, feel free to pack up your stuff, go home. Guys, don't forget do not forget to do that homework. Okay?
When's it?
Monday.
Need to record it.
Yeah.
Do it on Australia.
Yes.
Yeah.
You're doing four films.
No problem.
You have to post on YouTube.
I will.
Okay.
I'm not even kidding. I'll
Okay.
send you guys the link.
Yes, and then I'll tell everyone if they need help with following.
Post on his.
Follow.
Wait, he's not gonna show this to the class. is he?
Subscribe.
Okay, good.
Subscribe and like.
I'm gonna put
below.
an outro. Don't forget to like and subscribe.
Yeah, don't, yeah. Don't you need a, like, the geo at the beginning, the piano.
Guys, before you leave, everyone. Sorry.
But you need like a nice like math question.